Welcome. This video covers the basics of multiple linear regression in SAS. We already looked at simple linear regression, which just tries to relate one predictor variable to the response in a linear function. Well, we could also add in other predictor variables to try to model that response. And so generally speaking, if we're trying to do a linear regression model, we try to predict the average response through a linear function of our parameters here. And so we can include as many of our different x variables as we want. We can use procGLM to fit any of these models, which is wonderful. Let's look at an example, some of these example models that we could try to fit. You may have heard the term curvilinear regression, not my favorite term, but this just basically means that you're going to include quadratics and cubics and that kind of thing in your model. So one of my predictors here is x. My second predictor is x squared. So it's that same variable, but we're going to include a squared term for it. So this is still linear regression because this is linear in my parameters, but we're able to fit a quadratic term, a quadratic x term in our model. You can also include multiple predictors as well, so I can have x1 and x2 in my model. And what this does is it tries to fit the best plane through our data. And we can include things like two predictors and an interaction. So here I have my x1, my x2, and then I have an interaction term between the two. And this just allows sort of the surface that I'm fitting between my points to be more malleable. It can change a little bit more. And really what we're trying to do here is fit a saddle through the data. But I just want to really get across to you the different types of models you could fit. You can have as many predictor values as you want over there on the right, as long as you have enough observations to fit the model. And you can include curvilinear regression with interaction terms and all these other things as well. So you can combine a lot of different ideas into one model. For inference, we basically always assume that our error terms over here on the right, these are always going to have the assumption of normal distribution, mean zero, variance sigma squared. Again, all of that's sort of beyond us at this point. Just know that that is an assumption that is made when you do your basic multiple linear regression models. All right, we already have this wonderful data set that has a bunch of numeric variables, so we could try to fit some of these more complicated models using that data. So we'll stick with that stock market data. We have our response variable as all ords, and we can use any of these x's, any of these predictors to try to model that thing. Let's start by doing a curvilinear regression model. Using a model that's quadratic in the retail variable. Whenever you do quadratic models and these sort of curvilinear regression models, you should probably standardize your variables. We talked about standardizing before, so you subtract off the mean, divide by the standard deviation. That's something you should generally do whenever you include quadratics and higher order terms in your model. We're not going to do that here just for simplicity, though. Here's how you would fit that model in SAS. So we're still going to use procGLM. We're just going to do retail and then retail times retail to give us retail squared. That's all we got to do is just change what model we're using by just changing what we have on the right-hand side of that equal sign. Here's what the plot looks like for this and the fit that we get. So this is the quadratic line that's fit by the data. So that's some beta naught, some beta 1, and some beta 2 associated with this model. And you can see here that when we only have one x, it's really easy to produce a nice error bound around this. So I can get a nice plot that gives me, again, this is a confidence interval for the mean response, and then this is a confidence interval for a future response at a particular x value. So that's really nice to see. It looks like this is roughly fitting right through the middle of the data, so that's also a good idea as well. Here's the output from that. So just like we saw before, there's this p-value up top, and this is our model utility p-value. So this is just seeing, is our model useful in some way to predict the data? And our p-value here is small, so we would reject h naught. So we'd reject that all of our parameters here is 0 in favor of the alternative that at least one of them is not 0. So something in our model is useful for predicting our response. Just like before, we have r squared representing the proportion of variation that is accounted for by our model. And then the root MSE is a measure of the variability in the data. Down here at the bottom, we have the actual coefficient estimates that we use to get that curve that we saw plotted on the previous plot. And then we also have p-values to test the slope terms for our different retail and retail squared variables. We can see here that both of these are pretty small, so that gives us an idea that this curve, this non-linear relationship is important. So looking at the actual curve here does give us something above looking at just a line through the data. And then, of course, we also can have confidence intervals for those slope terms as well. Notice that neither of those confidence intervals contain 0. As always, should check your assumptions. We should see rough patterns in all of these plots here. So we just hope to see no real patterns, so just sort of lines or values that are just spread out. We do see a little bit of a trend over here, but other than that, things are looking pretty good. And just like before, we hope to see a straight line in that, what we call a QQ plot here. We hope to see a rough bell shape down at the bottom. Things are looking okay in that front here. So that's an example of a curve linear regression model. We could also fit one with an interaction. So here I'm going to include retail and gold in my model as predictors, and as well as their interaction. To do this, again, all we need to do is change what's on the right-hand side of our equal sign. So now I have retail, I have gold, and I have retail times gold. So I'm getting their interaction as a predictor as well. This is a lot harder to visualize the actual fit since we have two variables now. This is what's called a contour plot that gives us an idea of the estimated value of our response for a given XY combination. So for instance, if I'm looking at a retail of 3,000 and a gold of 1,500, I can sort of map to where that is here, and you can use these blue lines to get an idea of where you're at. So this is somewhere between 8,000 and 9,000. So you'd guess maybe that's about 8,500 for the prediction of all ORDs for a retail of 3,000 and a gold of 1,500. Not as easy to look at as our one-dimensional plots, but this is how we can visualize our relationship here. Here's the output, just like we saw before. That top part is just going to give us an idea of whether our model is useful or not. It is in this case, since our p-value is very small. Just like before, we have r² and root MSE. We have our estimates for the model. We have our p-values for tests. We have our confidence intervals. So basically, we can look at the same kinds of things in all of these different models. Just like before, we check our assumptions. We hope to see rough patterns, or roughly no patterns in these residual plots and this top left one. And then we hope to see a straight line in this QQ plot and a bell shape down here. So everything is looking good in terms of our assumptions for this model. All right, remember that one of the great things about using regression models is that it allows us to do prediction. So we can predict for a future value for, say, an X1 and X2. So for a retail of this and a gold of this, I can predict what all ORDs might be. And by default, SAS is going to give us predictions for every X combination in my data set. So for every gold and retail combination I have in my data set, I can get out a prediction. However, sometimes you want to predict for combinations of X1 and X2, or gold and retail in this case, that aren't in my data set. I want to get the estimated value of Y. I want to get a prediction for the mean Y or the future Y for a given gold and retail that I don't have in my data set. Well, one thing you can do to get those predictions is add in missing observations to your original data set that you go to fit the model with. So for instance, I can add in new values of gold and retail to my data set as long as I include no Y value, no all ORDs value in this case. SAS will not use those new observations that I'm adding in the model fit, but it will still do prediction for those. So essentially we can do this little workaround to get these predicted values. We've seen how to combine data sets that are very, very similar. So here I'm going to create a temporary data set using in-stream data like we did before. So I'm going to input my three variables, although I don't really need to input the Y variable if I don't want to, but I'm going to input my three variables I'm using in my model. And now I have combinations of gold and retail that I have of interest. So gold of 2,000 and retail of 3,300, gold of 2,200, retail of 2,500. I want to add those into my data set so I can get predictions for those combinations. Notice that I'm using periods here. These periods, these periods are representing missing observations. For numeric variables, periods are missing, right? So I'm not including new Y values. These are not going to be used when I actually go to fit my model. We saw how to use the set statement to concatenate two data sets. So I'm just going to use the set statement with the original banking data set and then temp. So I'm going to put that temp data set right on the bottom. Any other variables that are in banking that were not in temp will just have missing observations. And that's why we really could have left off all ORDs here, because it would have just defaulted to a missing value anyway. But I've now replaced my banking data set with my banking data set and these two new observations as well. Now when I go to fit the model and I use CLI or CLM, I will get predictions not only for the ones in my data set, but for these new values that I just added. So for instance, down at the bottom, if you looked at the very bottom of the output here, there'd be 2 new observations where there are no predicted values. So these are not being used in the model fit. Sorry, there are no observed values, but there are still predicted values. And we still get confidence limits as well. And so that's really, really useful to see. So let's just map these on this chart real quick. So remember that we had 2,000 and 3,300 for this first one. So 2,000 must have been for gold and 3,300 for retail. Let's just double check that. Yep, for gold and then retail. And so that should end up being somewhere around here, right, in our contour plot. And we can see that that's pretty close to this line that's representing 10,000. And so our estimate here is 9,700. So that does make sense with what we're seeing over there on that plot. And then this over here is a confidence limit for the all ORDS value, for a future all ORDS value at that combination of gold and retail. All right, let's jump into SAS and see a quick example. All right, here we are in SAS. We will go ahead and copy this previous GLM statement. We'll still use this wine data set. I'm just going to add some new variables over here on the right. So I have pH. Let's go ahead and add in that alcohol variable we had before. Let's add in our citric acid as well. Oh, sorry, I used the wrong quote there. And let's add pH squared, just for the fun of it. I won't ask for prediction limits here. We'll just fit this basic model here. This may take a little while to run because it's got to do a lot of estimation here, so we'll see how long it takes. Yeah, that wasn't that long. And here we go. We have our model utility p-value up here. We can see that this is significant, so something in our model is useful. We can go down here and look at our parameter estimates and see that we have significant p-values on all of these. So actually every term in our model appears to be important and useful. We could keep going on down. We should see roughly no pattern here. It's a little bit hard to tell, but that line is going sort of through the middle of the data. And then we want to see a straight line here, so that's pretty good as well. These are more residual plots, so again, we hope to see no real pattern between any of these. And maybe there's a little bit of a pattern here, but not too bad. So our model appears to be fitting pretty well. We have significance between all of these predictors, and so that's allowing us to have an idea about what's important for the quality of our wines. We could also use this model like we did before for doing predictions if we wanted to. All right, to recap, we now have an idea about doing correlation analyses, simple and multiple linear regression. These are some commonly used ways that we can try to understand how predictors are related to responses. And really, this wraps up this course. We now have a pretty reasonable idea how to take in raw data, summarize it in meaningful ways, and do some common analyses. Hopefully you can see how useful software, and especially the SAS software in this case, is for making really interesting and useful conclusions about your data.